Alright, what's up everyone? Welcome back to Structure Free Learning! And in this video, we're going to do an example problem analyzing a statically determinate frame. We'll be given the frame geometry and loading, and what we're going to do is calculate the support reactions and draw the internal loading diagrams. So the normal, shear, and bending moment diagrams of this structure. So this is what our structure looks like. Alright, so here's my structure. I have a pin support at A, I have a pin or a hinge at B, and then at point C I have a fixed or moment connection, and then at D I have another pin support. So one of the first things that we need to do is check the determinacy of the structure. And so if there's no closed loops on the structural frame, one of the things I can do is just separate at any of the pins or hinges and count equations and unknowns. And so here is my schematic for the determinacy. So this is what my system looks like if I separate at the pin at B, and here I would have reactions, if you will. So I'll call this like BY and BX that basically connect the hinge or the pin together. There's no moment resistance at a pin because it's free to rotate, and so here equal and opposite. And so now I have two separate free body diagrams. And I have support reactions here, AY and AX. And then here I have DY and DX, like this. And here now, by counting my number of unknowns, I would have 1, 2, 3, 4 at the hinge, 5, 6. And my number of equations, I have two separate free body diagrams, and I have 3 equations per free body diagram. So I have 6 equations. So I have 6 unknowns, 6 equations, and therefore this is statically determinate. Alright, so now that I know that it's statically determinate, I can use my equilibrium equations, and really any one of these 3 diagrams, the entire structure, the separated free body diagram here on the left, or the separated free body diagram of member BCCD on the right, and I can use any of those to determine my support reactions using equilibrium equations. So if I look at the entire FBD here, and if I take moments about A, I can go left to right. I notice that the resultant here is 2 times, well, I have a 3, 4, 5 triangle, so this length is 5 meters right here, and so the resultant is 2 times 5, this is 10 kilonewtons, and this, the line of action, is perpendicular to this member AB. Then my arm, in this case, would be here to point A. This is 2.5 meters. And so now I would know that I have negative 10 kilonewtons times 2.5 meters. And then I have my 5 kilonewtons also causing a negative moment, 5 kilonewtons times 5 meters minus 5 kilonewtons times 5, 7 meters plus dy times 9 meters equals 0. And here I have one equation, one unknown. I don't have to include dx or ax because the line of action goes through point A. Here dx is equal to, I get a positive 9.444 kilonewtons, which means that the direction that I drew it is good. So this dy is 9.44 kilonewtons pointing upwards. So now I have that. I can go ahead, I can go to any, maybe I go to my next free body diagram. I've determined dy. I could probably go to this whole structure again, do some of the forces in the vertical, and get the support reaction AY if I wanted to. That's one option. I will, let's see, what did I do? I looked at this right free body diagram, and I did some of the moments about point B. So here's the right side of that free body diagram again. And so now if I look at this side and I take moments for this diagram here, if I take moments about point B, I would have dy times 6 meters plus dx times 4 meters minus 5 kilonewtons times 2 meters minus 5 kilonewtons times 4 meters equal to 0. And in this case, we know that dy is this 9.444 kilonewtons. And when I solve for dx, I will get a negative 6.67 kilonewtons, which means that the negative sign indicates it's opposite of the way that I drew it. So this should actually be 6.67 kilonewtons pointing to the left. And then using the same right side, this drawing right here again, I can do some of the forces in the horizontal. And I would have negative bx plus dx equals 0. I'm using, notice I put a positive dx just because I'm using this drawing and I want my equation to reflect the drawing. And so here, this would tell me bx equals dx is a negative 6.67 kilonewtons. Therefore, bx is 6.67 kilonewtons, pointing to the right. And then similarly, I can do some of the forces in the vertical. And here I would have by minus 10 kilonewtons plus dy equals 0. And here, dy was 9.444 kilonewtons. And now when I plug and chug, I will get that by is equal to a positive 0.556 kilonewtons, which means that, yes, the direction that I have this by drawn in is good. It's 0.556 kilonewtons pointing upwards. And so these are my results so far. I have, last but not least, I can go ahead, I've got plenty of choices here. I know dx and dy. I could use this drawing right here, this drawing right here to determine ax and ay, or I could go back to this whole drawing here and do some of the forces in the vertical and horizontal to get ax and ay. It's up to you. It's your own choice. It's your own adventure. Here, I will choose this side of the drawing, the left side of my separated diagram. And I can just sum forces in the horizontal and vertical direction and get ax and ay directly because I know by and bx. And so here in the horizontal direction, I would have ax plus bx. And this I could break up into a horizontal and a vertical component like that. Yes. And here this ax plus bx plus 10 kilonewtons. This component right here is 10 kilonewtons sine theta is equal to 0. And based on my 3, 4, 5 triangle, I know that sine theta is 4/5. And I knew that bx is negative 6.67. And so here, if I go ahead and I plug and chug, I would get ax is a negative 1.33 kilonewtons. And that would indicate I have 1.33 kilonewtons pointing to the left. And then similarly for some of the forces in the vertical, I would have ay minus by minus 10 kilonewtons cosine of theta equals 0. And this would tell me, let's see, by was positive 0.556. So I'm going to put a 0.556 kilonewtons in there. And the cosine of theta is 3/5. And so when I plug and chug, I would get that ay is equal to a positive 6.556 kilonewtons, which is 6.556 kilonewtons pointing upwards. And these are my other two support reactions. And you'll see that if you went and you did the same thing after you got dx and dy, if you did the sum of the forces in the vertical and horizontal for the entire structure here, you should get the same result. So here's my structure with the support reactions drawn in with their correct magnitude and direction and my whole loading. And so I want to find the internal shear moment diagrams and the axial force diagrams for members A, B, B, C, and C, D. One of the things I need to do is actually choose a local coordinate system, which is really a fancy way of saying figure out what's the beginning and end of your beam. All right, and so you have to say, oh, I'm going to go left to right, but what is left and what is right? And so here, if I'm going here for member AB, I'll just choose I'll choose A as the beginning of the member and B as the end. So I'll go left to right like this. I could go the other way, but it's up to you. Here for member BC, I'll choose going left to right like this. So B will be the beginning of that member and C will be the end. And then similarly for CD, I'll just keep going clockwise. I'll go left to right like this. Now, angled members can be a little bit tricky. And really, especially in a case like this where you have a vertical and horizontal support reaction, you have to translate these into normal and shear to the member at the beginning of the member at A. So a lot of times what we'll require is for you to do like joint equilibrium so that you can determine what the internal normal, shear, and moment are at the beginning of the member. So to figure out the internal shear and moment that I want to start at for member AB, I'm going to cut out and apply and look at joint equilibrium of joint A. And so here I'm going to say I cut just before the distributed load on the member starts. And I'm going to look at and isolate joint A here. I'm going to really exaggerate joint A here. Yes. Here at joint A, I have a 6.556 kilonewtons acting upward on the joint. Here I have 1.33 kilonewtons acting to the left. And then I have this member here that's going to be, this blue line would be the face of the cut of that member. And again, acting normal to the face of that cut would be this NA. I would have a shear that's acting parallel to the face of that cut. Right here, I'll call that VA. And then technically I could have a moment right here, MA. Right here. All internal loads at the beginning of the member here. Equilibrium of the joint. And so I would have equilibrium. This joint cannot be moving anywhere. It's pinned and it's not moving left or right. And so I can apply my equilibrium equations to solve for NA, VA, and MA. We'll start with the simple one. If I take moments about this joint, well, all my forces are acting at a single point, so they don't cause any sort of moment. And so MA, this moment at the beginning of the member, AB, is equal to 0. Yay! All right, so that's not bad. And so now it's like kind of like method of joints in what you learned in truss analysis. And so here I can remember that, let's see here, I know that I have, this thing is a 3-4-5 triangle. So this is a 3-4-5, and this it would be an angle theta. And similarly here, if I continue this line like this, and I draw some horizontal and vertical lines right here, this is the angle theta right there. Yes. And so now here, let me distinguish my line of action here and here. The red and blue, and then here I have another blue line like this and like this right there. Ah, yes, this always helps me figure out what my angles are. And I'll notice that my angle theta also happens here. And let's see, this is 90, this is 90, so this is also theta like this. Yes. And now I could just go sum of the forces in the horizontal and vertical and break up NA and VA into horizontal and vertical components, and that you could do that. And you would end up with two equations, two unknowns, and you have to do a little bit more algebra and solve for NA and VA. So that's definitely an option. One other option is I could align my sum of the forces in this direction parallel to NA. So here, I would say sum of the forces in this direction parallel to NA equals 0. And what it does is it decouples the equations for NA and VA. So I would have NA alone. So this would be NA. And then if I look over here, let's see if I break it up like this. If I break up like this, I know that my angle theta, just, my blue line here is parallel to that line right here. So this is my angle theta right there. And so in that NA direction, I would have a negative 1.333 cosine of theta. And then for this, for my 6.556 kilonewtons here, I would break up my triangle like this. And I know that this is also that angle theta. And so I would have plus 6.556 kilonewtons sine theta, and all this equal to 0. And again, from the 3-4-5 triangle, I know that if I look over here, a cosine theta is 3/5, sine theta is 4/5, and so now when I plug and chug, I will get that NA is negative 4.44 kilonewtons. And then similarly, now I will do the same. I'll do sum of the forces in this direction like this, positive, parallel to that VA, the shear. Sum of the forces equal to 0. And I would have VA minus 1.333 sine theta minus 6.556 cosine theta equals 0. If I solve for this, I will get VA is equal to 5 kilonewtons. And these are the values that I would start with from my internal loading diagrams here. So for member AB. And the way that we would interpret this, check this out. I've used joint equilibrium to figure out my starting internal loading values. And so if you can imagine here, if I look at member AB, so if I look at member AB as if I cut it out. So here I cut it out, boom, like this. So I have cuts here and here, like that. At the beginning, going left to right, right here, at the very beginning, I have these internal loads at MA for the moment at that support, or at the moment at the beginning is 0. I have a negative 4.44 kilonewton internal normal. That means it's causing compression on the face of the cut. So I have 4.44 acting like this. And then I have a positive internal shear. And on the right side of a cut, I would have, boom, right here. This would be 5 kilonewtons acting upwards. And so this is my beginning for my shear and moment diagram. I can now draw the shear and moment diagrams for this member. I have a distributed load on the member here. I don't need any of the information on the right. Go to watch a video on shear and moment diagrams, preferably one from Structure Free. Boom. I want to draw vertical lines at discontinuities, which are beginnings and ends of distributed loads, as well as where I have concentrated forces and moments. So I would have, boom, these vertical lines here. Yes. And then I would have, let's see, a normal force diagram. And that normal force is a negative 4.44 in compression. So my normal force diagram, boom, normal, kilonewtons, units. There's no axial loading along the member. And so I would have a constant internal normal of negative 4.44 kilonewtons. And so that means this starts at negative 4.44 and goes all the way across to negative 4.44. And that's what my internal normal force diagram looks like for member AB. Then I can draw my shear diagram. And for my shear diagram, let's see. I have a internal shear of 5 kilonewtons pointing upwards. So boom, I'll put 5 kilonewtons right here. That'll be a positive 5. My distributed load is a constant. And I know that my shear diagram is one antiderivative away. Therefore, my shear diagram will be linear like this. And it will be going down. It's linear. It's going down. The area under the distributed load, this distance, this length, 5 meters. And so it's going to change 10 kilonewtons. So I'm going to go from 5 to negative 5. Negative 5 kilonewtons. And then for my moment diagram, let's see, it's probably useful to identify where my shear would be 0. So here the shear is 0. Let's see, what else would be useful here? It's the location where the shear is 0. Now you can look here and everything is symmetrical, so I would suspect that this distance should be 2.5 meters. If you didn't know how to figure that out, let's say I call that distance A. And the thing I do know is that there's this relationship way back when you started learning shear moment diagrams, was that the change in shear is equal to the area under the distributed load. And it was represented by an integral symbol here. But going from here, going left to right, from here to here, the change in shear is 5 kilonewtons. And then here, it has to be the same as the area under the distributed load. And so if I go up here, there is some distance A, where this area is equal to 5 kilonewtons. So that area is base times height. So area under the distributed load, in this case, is base times height. So it would be A times 2 kilonewtons per meter. And when I solve for A, I get A is 2.5 meters. And so that's how I know A is equal to 2.5 meters. And that means, let's see, I have no concentrated moment, or my internal moment at end A is 0. So here, boom, I start at 0. My shear diagram is linear, therefore my moment diagram is parabolic. X squared, the amount or the change in moment, is equal to the area under the shear diagram. And so the area under the shear diagram here is 1/2 the base of 2.5 meters times 5 kilonewtons. And that is equal to 6.25 kilonewton meters. And so I have a positive area. That means I go up to 6.25 kilonewton meters, right there. And now the question is my diagram, should I be choosing for my diagram, should it look like this parabolic or something like this parabola? And the way we know that is from this relationship here, dm dx equals v, right here, which really just means that the slope of the moment diagram is the value of the shear. And so here at this point I have a shear value of positive 5, which means that my slope here should be positive like this. And then here I have a shear value of 0, which means my moment diagram should have a slope that's horizontal there. And therefore this line at the bottom is dead to me. Yes. And then very similarly, if I look here, it's going to be parabolic again, going here, going from left to right, from the middle to the end of member AB. I have to be horizontal here. I have to have a slope that's -5 here. And so boom, my moment diagram will look like this. All right, so that's member AB's internal normal shear and moment diagram. And so now we're going to have to repeat the process that we just went through for members BC and member CD. One thing that I want to be able to do is translate these internal load values here at the very end of my member onto the member itself. And so here I can say, at the end here, at the very end, if I make a cut at B inside the member, I would have a normal force of -4.44 kilonewtons. That means I have a force causing compression on the face of that cut of 4.44 kilonewtons. Here I have a negative shear of 5 kilonewtons, -5 kilonewtons. And on the left side of a cut, a positive shear goes downwards, but I have a negative value. So in this case, this shear would be acting upwards of 5 kilonewtons like this. And then I have a moment that's 0, so I don't even need to draw that. And what you'll notice is that if I look at this whole drawing, the whole member itself, even the member itself is in equilibrium. Okay, this member itself is in equilibrium. So if I did some of the forces in the vertical direction or in the direction parallel to the shears, then I would have 10 going upwards and 10 coming down. If I did some of the forces in the quote horizontal or in the direction parallel to the normal forces, you'll notice the member is also in equilibrium. And that's also true. So whenever I cut out a member, the member itself must also be in equilibrium. And so I could have determined these end internal loads, if you will, at point B just from doing equilibrium of the whole member as opposed to drawing the shear and moment diagrams if I wanted just that point. That was a lot of information. All right, hopefully that was useful. All right, so we'll move on to members. This is a really long example. We'll move on to members BC and CD next.